Good afternoon all. Today we are going to discuss about balancing chemical reactions. Right, that is the topic for today. So we are starting a new section today. Today onwards, we are going to discuss about 4 types of chemical reactions. Right, here you can see here. First, we will start up with the thermal decomposition reactions. Then we go towards the precipitation reactions, acid base, and the redox reactions. Our main discussion for today is this thermal decomposition. Let's discuss about how to write the thermal decomposition reactions and how to balance those stuff, and then how we can use those thermal decomposition reactions in chemical calculation questions. Right, that is the things we are going to discuss today. Let's start about the discussion about thermal decomposition reactions. Right, on this topic we are going to discuss about the thermal decompositions of metal hydroxides, metal carbonates, metal bicarbonates, and metal nitrates. Right, those 4 are the type of salts, type of compounds we are going to discuss under the thermal decomposition trends. Right, okay, let's start with the proceedings. Right, first of all, when we are coming up with these metallic compounds, metal related compounds, right, first we divide the metals of your activity series into 3 sections, so that it is very easy to study about the thermal decompositions if you are to follow in this trend. Right, okay, let's start with that. Right, we know the activity series of metals now. Right, the thermal decompositions of hydroxides, carbonates, bicarbonates, and nitrates depends on the position of the metal at the activity series. Right, so let's first discuss about the activity series. Activity series of metals. Right, so when it comes to activity series of metals, right, so you know the stuff now. So these are the activity series, right? The metals of the activity series: potassium, sodium, calcium, magnesium, aluminium, zinc, Fe, cobalt, tin, lead, hydrogen, mercury, silver, platinum, gold. Right, these are the metals of your activity series. Right, let's divide this into 3 sections. Right, so these guys, the first elements of the activity series, are known as active metals. Active metals. Right, actually not only the sodium and the potassium, but all the elements in your S block other than the lithium. Other than lithium, all the elements in your S block, the group 1 of your S block belongs to active metals. Right, so one can say all elements of group 1 other than lithium. Right, those are referred to as active metals. Right, then the final 4 guys, right, those are referred to as inert metals. Those are referred to as inert metals. Right, here you have the active metals, all the elements of group 1 other than lithium, and you have the inert metals, right, at the bottom of the activity series. Right, all the elements other than the active metals and the inert metals, all the metals other than the active metals and the inert metals are actually known as, right, actually known as moderately active metals. Moderately active metals, right? Moderately active metals. Even the lithium comes under those moderately active metals. Sorry, we have a problem there. So we have another one here, the copper. Copper is also known as a moderately active metal, right? This is the position of hydrogen, right? This is the position of hydrogen in the active series, right? After the hydrogen, right, you have copper, mercury, silver, platinum, gold, right? So copper is also comes under moderately active metals, right? First, we divide your active series of metals into 3 sections. Then it is very easy to follow the trends of the thermal decompositions of these salts, right? Okay, so let's discuss about one by one. First, let's start with the thermal decompositions of hydroxides, carbonates, bicarbonates, and nitrates of active metals. Let's start with that. Thermal decompositions of active metal compounds, right? Here we are actually referring to hydroxides, carbonate, bicarbonates, and nitrates, right? Okay, so what are the active metals? Basically, other than lithium, the group 1s are known as active metals. So that we have 4 elements there, right? Other than lithium, the group 1s: sodium, potassium, rubidium, and cesium, right? These are the metals which are referred to as active metals, right? So we are going to discuss about the thermal decomposition of these guys: carbonates, bicarbonates, hydroxides, and nitrates, right? Okay, actually when it comes to active metals, right, they are hydroxides and carbonates won't decompose, right? Active metal, hydroxides, and carbonates won't decompose. That means like this. If you are trying to decompose the sodium hydroxide by applying heat, nothing will occur. Nothing will occur. No decomposition. Even for the potassium, rubidium, and cesium, the same thing. No decomposition can be observed with the active metal hydroxides. Right? If you are trying to decompose the carbonates of active metals, same thing. No decomposition, right? No decomposition occurs with the active metal carbonates. Not only the sodium carbonate, but also potassium carbonate, rubidium carbonate, cesium carbonate. Those won't get decomposed. Right? But when it comes to active metal, bicarbonates and nitrates, those will decompose, right? Okay. Active metal, bicarbonate, and nitrates that decompose as shown below. Right? If you are trying to decompose the sodium bicarbonate, that solid, what will happen? It will decompose into sodium carbonate, the CO2 gas, and the H2O gas. Right? So if you are trying to decompose if you are trying to heat the sodium bicarbonate, decomposition will occur to give you the carbonate, CO2 and H2O. You can just balance by inspection, right? Just balance the atoms in the both sides, right? So you have 2 of these sodiums, so you can put some 2, and then the other things are balanced, no? Right. What happens to the nitrates? So if you are trying to decompose the sodium nitrate by applying heat, it will decompose, giving you the sodium nitrite solid and the O2 gas. O2 gas. Basically, by these decompositions, the solid mass will reduce, right? The amount of mass will reduce as gaseous products are forming, right? So we can balance this stuff as well, right? So by applying 2, it will be balanced, right? Not only for sodium, but also for all of these active metals, right? They are bicarbonates and nitrates will follow this trend. If you are thinking of potassium bicarbonate, it will decompose to give you potassium carbonate, CO2 and H2O. If you're thinking of potassium nitrate, it will decompose into potassium nitrite and NO2. Like that, with rubidium as well as cesium, these trends will be followed. Right? This is how the active metal compounds will decompose. Basically, we are concentrating on the hydroxides, carbonates, bicarbonates, and nitrates under this topic, right? Okay. So hydroxides and carbonates won't decompose but the bicarbonates and nitrates will decompose for these 4 metals, which are known as active metals, right? It is all what you should know about the active metals compound decomposition, right? Let's come up with the moderately active metallic compounds, right? Okay, part B is about moderately active metallic compounds, right? Thermal decompositions of moderately active metal compounds. Actually, what are the moderately active metals? Right? Under moderately active metals, right? All the metals other than those 8, the 4 active and the 4 inert are concerned. The 4 inert guys are mercury, silver, platinum and gold, right? Right. Now we are going to discuss about how the other metals than these guys will decompose, right? So let's discuss about those, right? Basically, when it comes to moderately active metals, right, normally they tend to form their respective oxides, right? So let's discuss. It's like this. So if you are trying to decompose the magnesium hydroxide, right, what happens is actually it will decompose, giving you the oxides of the constituent elements. So you have the magnesium here and the hydrogen here. So the decomposition products are the magnesium oxide and the hydrogen oxide. The hydrogen oxide is H2O, right? So you will get the magnesium oxide plus the H2O. Normally the oxides will be formed by the moderately active metal compounds. So if you are thinking of the carbonate, magnesium carbonate, right, it will decompose, giving you the magnesium oxide and the carbon oxide. Magnesium oxide and the carbon oxide, right? So the magnesium oxide and the carbon oxide. So oxides of the corresponding constituent elements will be formed, right? So you can balance the stuff now, not that much hard now. So 2 hydrogens are appearing, so one can come up with 2 here, right? So it's like 2 of oxygens, but you have more there, no? So you may have to come up with 4, right? So that is also not good, right? So we have a problem here, no? Magnesium oxide is coming up with some 2 there, no? Right? So magnesium is 1, 2 oxygens and 2 hydrogens, no? So it is balanced actually, right? Okay, this is the magnesium carbonate situation. That is also balanced, right? So what about the bicarbonate and the nitrate? So when it comes to magnesium bicarbonate and the magnesium nitrate, the 2 guys are special. 2 guys are bit special, right? I earlier said normal trend is giving you the oxides of the constituent elements, but with these 2 guys, some special things can be seen. So when it comes to magnesium bicarbonate, right, it won't produce the magnesium oxide as the first product, but first it decomposes, giving you the magnesium carbonate, right? So that is special, right? We are expecting some oxides to occur, but magnesium carbonate is the first decomposition product of magnesium bicarbonate, right? So magnesium carbonate and the hydrogen oxide and the carbon oxide will be formed, right? Not the magnesium oxide here, it is the magnesium carbonate, but for the other 2 elements, they will give their respective oxides, the hydrogen oxide and the carbon oxide, right? So CO2, the carbon oxide, and the hydrogen oxide. So some specialty is there with the carbonate, right? Some 2 VIP situations, right? So magnesium carbonate, CO2 and the H2O. I think the numbers are balanced, no? 6 oxygens are there, yeah, things are balanced, right? There is some special situation with the magnesium bicarbonate, right? So when it comes to magnesium nitrate, so magnesium nitrate, not the nitrate, it's the magnesium nitrate. When it comes to magnesium nitrate, so normally bicarbonates are, right, as aqueous solutions in this case, right? Okay, when it comes to magnesium nitrate, what will happen, right? Magnesium nitrate. So magnesium nitrate decomposition is a bit special. So not only not only they will give you the oxides, but also the O2 gas. That is specialty with the nitrate decomposition, right? So magnesium oxide, as we are expected, and the nitrogen oxide, NO2, Not only those, but the O2 will also produce. The O2 will also produce. That is a specialty with the magnesium nitrate decomposition. Not only the oxides, but the O2 gas will also produce there, right? So we need to balance the stuff, right? If you are coming up with 2, it's not good, right? So you may need to come up with 2 here as well, right? So 2 here and 4 here, no? And that is how you're supposed to balance the stuff, right? There, the oxygen gas will also evolve, right? So those are the 4 kinds of decompositions you should know on this topic, right? The magnesium hydroxide, carbonate, bicarbonate, and nitrate. All the things will get decomposed under the moderately active metals, right? Not only for the magnesium, but also for the all the other metals other than these guys, right? So for the lithium hydroxide, same trend will occur. Lithium hydroxide will decompose to lithium oxide and the H2O, the metal oxide, and the CO2 for the carbonate, like that. So if you are thinking of copper, the same thing will occur. Copper hydroxide will decompose to copper oxide plus H2O. Copper carbonate will decompose to copper oxide plus CO2. If you are thinking of copper bicarbonate, it will decompose to copper carbonate, CO2, and H2. For the copper nitrate, it is copper oxide, NO2, and O2, like that, right? So all the metals other than these 8 guys will follow this trend, right? These trends when they are supposed to decompose, right? This is how the moderately active guys metal compounds will decompose. Normal general trend is giving you the oxides, and these 2 cases you are with some VIP situation, right? So these 2 guys are with VIP, yeah. Just remember that. This guy not only giving you the oxides, but also O2 gas will be released. But with the bicarbonate, right, of the moderately active metals, right, the metal oxide is not formed as the first product. It will be the metal carbonate, right? Those are the 2 different things you can observe with the VAB guys at the thermal decomposition of moderately active metal compounds, right? Okay, so that is about that. Let's discuss about the third stuff, how the inert guys, the inert metal compounds will decompose. Let's discuss about that thing as well. Part C, thermal decompositions of inert metal compounds. Right? We have only 4 inert metals, right? What are those 4? The mercury, silver, platinum, and gold. These are the inert metals. Now we are going to discuss about how these guys are to get decomposed when we are to supply heat. How the compounds of these guys will decompose when you are to supply heat, right? The special thing here with these guys is actually these guys are very keen to be alone. These guys are very keen to be alone, right? So there's a national anthem for these guys, right? National anthem එකක්. හරි. මිල්ටන් මල්වාරච්චි කියන සින්දුවක් නේද? තනි වී සිටින්නයි මා අදහස් කළේ කියලා. අන්න ඒක තමයි මේගොල්ලගේ ජාතික ගීය. හරිද? So these guys are very keen to be alone, right? තනියම ඉන්න තමයි කැමති කට්ටිය. හරිද? Right? So තනි වී සිටින්නයි මා අදහස් කළේ තමයි ඉතින්. හරි. So always when you are trying to decompose the compounds of these guys, right? So they prefer to be as alone as products. Let's discuss, right? So I write some note there. So inert metals are keen to be alone. So when decomposing inert metal compounds, right, they will come as alone metals, right? That means actually that means even the metal oxides will decompose giving the alone metal and O2 gas, right? It's like this. If you think of the silver oxide, those metal oxides will also decompose, giving you the silver solid and the O2 gas, right? Earlier with the moderately active metals, right, we haven't seen this kind of decomposition with the oxides. The final products were the oxides when it comes to moderately active metal compounds. The moderately active metal compounds decompose to give you the metal oxides and the stuff, right? Normally the metal oxides, not that, and that was seen in the carbonate situation, in the bicarbonate situation, but with the other guys you had came up with the metal oxides, right? But when it comes to inert metal things, the metal oxide will also decompose to give you the inert metal and the O2, right? That is the major difference of these inert metals compounds compared to the moderately active metal compounds, right? Let's discuss a bit more examples, right? Some more examples. So if you are to think of the decomposition of, let's think of the decomposition of silver carbonate. So then what will happen? So if it was a moderately active metal, it should give the metal oxide and the CO2. But as this one is silver is kind of a inert, the metal oxide will also decompose to give you the metal and the O2. Give you the metal and the O2, and CO2 will be produced, right? Those are the products. So if you think of silver nitrate, what are going to be the products? So as this one is an inert metal, right, it is not going to give you the metal oxide, but the metal and O2. And the nitrogen is also there, so NO2 will be also produced. Nitrogen oxide, right now? Okay, that is very clear. So not only for the silver, right? For all the four guys, the same thing will happen. With the mercury carbonate, mercury nitrate, the mercury, O2 and CO2, the mercury, O2 and NO2, those things are going to be the products, right? So let's come up with the mercury nitrate as well. If you think of mercury nitrate, what will happen? So it is not the mercury's oxide, it is the mercury plus O2, as it's an inert metal. Mercury is kind of a liquid, and the nitrogen will give you the nitrogen oxide, then O2, right? So that is how the products are to be formed. So you can balance the stuff by inspection, right? Okay, let's balance by inspection, right? So you have 3 oxygens, that it can't be balanced like that, no? So it should be 2 there. So 4 of these guys. So 6 of oxygens and 2 carbons, no? 2 carbons and 6 of oxygens, right? Not hard, that much hard to balance, right? So you have the silver here, 1 nitrogen and 3 oxygens, right? So it can't be 2 there to balance the 3, right? So 6 oxygens means we have to can't be 2 here. Balancing this stuff, right? So 6 oxygens are there and 1 mercury and 2 nitrogens, no? So 2 nitrogens here, the stuff are balanced, right? Okay, so this is how the decompositions, thermal decompositions will occur with the inert metallic compounds, right? Okay, right. Let's do some example. Let's do some exercise here, right? Before we are going for some calculation questions, let's do some examples. Write the balance, right? Thermal decomposition reactions for the following. Just try to write. Right. Number 1. Zinc carbonate. Number 2. Right. Potassium nitrate. Number 3. Aluminium hydroxide. Number 4. Mercury carbonate. Number 5. Right. Rubidium bicarbonate. Let's do 6 stuff, right? Number 6. Right. Copper. Right. Copper bicarbonate. So bicarbonates won't come as solids other than for the active metals, right? So let's copy like this, right? So let's try to write the equations for this. I will come with another one, 7. Right, come with potassium hydroxide as well. Right, okay, let's try to do one by one. Zinc carbonate. So first of all, right, just see with which category the zinc comes. Zinc belongs to the moderately active metals. It is not coming from the active 4, sodium, potassium, rubidium, and cesium. It is not coming under the inert 4, mercury, silver, platinum, gold. So it should be a moderately active metal. Moderately active. Right? Moderately active metal. So those will follow the oxide forms. Give you oxide forms. So zinc will decompose to give you the zinc's oxide, and carbon will give you the carbon's oxide. So the zinc oxide and the carbon dioxide, those are going to be the products, as this comes under moderately active metal compounds. So balancing is not that much hard. The things are balanced. This one, right? So potassium. First, think of this. To which category the potassium belongs to? Potassium belongs to active metals. Active metals. So the active metal nitrate decomposition. So active metal nitrate decomposes. Active metal nitrates will decompose to give you the nitrites, NO2 and O2. Sorry, nitrites and O2. Right? So the potassium will decompose to give you potassium nitrite plus the O2 gas. Right? Balancing is not that much hard, Lavai. Just by each session you can do the balancing. So 3 is there. That means first you need to come up with as an even number. So 6 guys are there. So it's balanced, no? Right. Next one. Third one. Aluminium. Aluminium comes under moderately active metal. Not belongs to the active 4 or the inert 4. So that will be a moderately active metal. So moderately active metal hydroxide decomposition. So the oxides will come up as products. The aluminium's oxide and the hydrogen's oxide. The oxides of the corresponding elements, constituent elements. Aluminium's oxide and the hydrogen's oxide, which is the H2O, right? So aluminium's oxide, Al2O3, aluminium 3 plus, and the oxide form is O2 minus, right? O2 minus Al3 plus the aluminium's oxide plus the hydrogen's oxide, that is H2O, no? Right? Just try to balance the stuff, right? So 3 hydrogens, 3 oxygens, right? So not good, right? So this can't be 2 here. 2 aluminiums, 6 hydrogens and 6 oxygens, right? So that is done, no? Okay, this one. Mercury. Mercury comes under inert metals. Inert metals. Comes under inert metals, no? So inert metal carbonate decomposition. So when it comes to inert metals, the metal won't produce the oxides. Metal won't produce the oxide. That will decompose to give you the metal and O2. And the other constituent elements will come up as oxides. So from mercury, you will come up we'll gain the mercury liquid, the metal and the O2, and with the carbon you get the CO2, the oxide, right? It's balancing, right? 3 of oxygens, that means it is better to count with 2 to get some even number. So it is easy to balance, right? So 2 carbons and 6 oxygens, no? That is okay. Like this. Next one. Rubidium bicarbonate, right? So rubidium, where it stands. Rubidium comes under active metals. Under active 4, rubidium is there. Sodium, potassium, rubidium and cesium. Those are the 4 guys belongs to the active category, right? Active metal. Active metal bicarbonate decomposition. So it will give you the carbonate. It will give you the carbonate, H2O and CO2. H2O and CO2. Right? Okay. Let's try to balance the stuff. I think it's 2. We'll balance the things, right? 2 hydrogens and 6 oxygens, right? So yeah, the things are balanced. This one, copper. To which category the copper belongs to? It is not belongs to the active category. It is not belongs to the inert category, right? That means copper comes under moderately active, right? So it's a bicarbonate decomposition. So moderately active metal bicarbonates, that is kind of a VIP situation. So metal oxide is not what you will get. It is the metal carbonate and hydrogen oxide, the H2O, and the carbon oxide, the CO2, right? So VIP situation with the, right, moderately active now, the bicarbonate things, right? So copper carbonate plus the hydrogen oxide is the H2O, the carbon oxide is CO2, right? Let's balance the stuff. So you need 6 oxygens, right? I think it is balanced. 2 hydrogens and 2 carbons and stuff, right? The things are balanced, right? Okay. Let's discuss about the KOH decomposition. Potassium. Potassium comes under active metals. The group bonds other than lithium. Sodium, potassium, rubidium, cesium. The potassium comes under that, active metals. So when it comes to active metal hydroxides, those won't decompose. Those won't decompose. So we can write they are no decomposition. No decomposition. No weight loss. No weight loss by heating. No weight loss. Right? Okay. So that is what happens there. Right? So this is how we are supposed to come up with the balanced chemical reactions regarding the thermal decompositions of hydroxides, carbonates, bicarbonates and nitrates. Right? Clear, no? Okay. Let's use the knowledge we have gathered, right, for a chemical calculation question. Right? Let's discuss how these things are to be used in chemical calculations. Right? Okay, let's go towards that. Right. Let's try to solve this one. This is a chemical calculation question related to thermal decompositions of metallic compounds. Right? Okay, let's see how to solve this one. So basically, right, when we are to solve this kind of a complex question, right, first thing to do is actually identifying the goal. identifying the goal, right? First thing is to identify the goal, right? What is the goal? Basically, the goal will be there normally at the first two lines of the question or at the last two lines of the question. So just see the first two lines of the question or at the last two lines of the question, you clearly see the goal and what is required there. That is your goal, right? Okay, so let's go to this. It says 46.8 grams of a solid sample containing magnesium carbonate and calcium carbonate was heated and completely decomposed. That things are given. The volume of gas collected is given, and find out the mass percentage of calcium carbonate and magnesium carbonate in the sample. So that is your goal. This is your goal, right? Finding out the mass percentage of magnesium carbonate and calcium carbonate, right? That is the goal. Just identify the goal. First thing to do in solving this kind of a question is identifying the goal, right? If you are with more than one chemical involved with the goal, normally just represent their number of moles as X moles and Y moles, as X moles and Y moles, right? That is how we are supposed to solve this kind of a question, right? So the two chemicals involved with this goal is the magnesium carbonate and the calcium carbonate, right? So let the moles of magnesium carbonate in this sample is equal to X moles and the moles of calcium carbonate is equal to Y moles, right? So if we were able to come up with the X and Y, those two values, basically number of moles, right? If you know that, if you are able to come up with those numbers, then as with the chemical formula, the G mole minus 1 data is there. So you can relate the G mole minus 1 data and the moles data to come up with the mass of the bond test substance, right? If you know this X value, you can combine that X value with the G mole minus 1 data of the magnesium carbonate to come up with the mass of the magnesium carbonate. So that as the total mass is given, you can come up with the mass fraction, then you can come up with the mass percentage as well, right? For the calcium carbonate is the same thing is valid, right? So that our first task is to actually to come up with the X and Y values. So first identify the goal of the question and put the number of moles of those compounds as X moles and Y moles. That is the first thing to do in this kind of a complex calculation, right? Okay, that is the first thing, right? Then the second thing is actually, right? First thing is identifying the goal and write the number of moles as X moles and Y moles. The first thing, right? Second thing to do in solving this kind of a problem is you have to write the equations. You have to write the equations related to the reactions occurring in the procedure. So write the equations, right? Second thing is to write the equations, right? Second thing is to write the equations, right? So let's copy the equations here. Equations related to this stuff, right? What are the equations? So the equations basically they are decomposing the magnesium carbonate and the calcium carbonate, thermal decomposition. So let's come up with those two equations, right? So the magnesium carbonate will decompose, giving you the magnesium oxide as it's a moderately active metal and the CO2. You need to come up with balanced chemical equation, right? So when it comes to calcium carbonate, it will decompose, giving you the calcium oxide and the CO2. right? The second thing is write in the needed chemical equations, right? Okay, that is done. Third thing, right? Then you have to identify, right? You have to identify the data points in your question. You have to identify the data points in your question. That is the third thing. What are these data points? Data points are the numerical values of chemicals you completely know, right? Data points are the numerical values of chemicals you have the complete knowledge, right? Let's see what are the two data points appear in this thing. Basically, to solve two equations, to solve the two unknowns, to solve for the two unknowns, basically you need two equations, right? To solve for the two unknowns, you need two simultaneous equations, right? So to come up with those two simultaneous equations, you need to identify two data points, two values they are providing you to come up with the simultaneous equation. Let's try to come up with those two data points, right? So the two data points of this question is actually, right, these two values, 46.8 grams. So about 46.8 grams, you know the chemicals appearing here completely. This 46.8 grams, they are the two chemicals appearing there is the magnesium carbonate and the calcium carbonate, right? So only these two guys are there, right? So that is one data point. And the second data point of this question is this one, this volume. Those are the two data points appearing in this question, right? To identify the two data points. That is very important. With these two data points, we are supposed to come up with two simultaneous equations, right? In terms of x and y, right? So actually, this is the total mass of the sample. This is the total mass of the sample. The total mass of sample. This is the volume of the gas collected. The volume of the gas collected, right? So I'll take it as amount of gas. Amount of gas, that is about the CO2, right? Gas is CO2 here, right? Those are the two data points appear in there, right? So let's come up with the stuff, right? So as you are with x moles of carbonate, magnesium carbonate, and y moles of calcium carbonate, right? That will provide you x moles of CO2 and y moles of CO2 as well, because 1:1 ratio, no? X moles of carbonate will give you x moles of CO2. Y moles of carbonate, calcium carbonate will give you y moles of CO2, because 1:1 ratio are appearing with both the equations, with the metal carbonate as well as and the CO2, right? So let's come up with the simultaneous equations. Let's come up with the simultaneous equations using the data points, right? So basically, normally, the simultaneous equations are to be built up for the masses or for the moles. Only for the masses or only for the moles, we are supposed to come up with simultaneous equations. Right? Basically, in terms of x and y, we need to come up with simultaneous equations, but they will be written only for masses or the moles. We are not going to write the simultaneous equations for volumes or any other things. They are for masses or for moles, right? So first thing, for the first data point, it is given as a mass, so we can come up with the simultaneous equation for this one, right? So let's come up with that, right? Simultaneous equations. right? The first simultaneous equation for the mass of sample, right? So in grams, right? In grams we are referring to. So mass of sample is actually a combination of the mass of magnesium carbonate and the mass of calcium carbonate. Only those two are appearing in the sample. So that mass of sample is a combination of magnesium carbonate and the calcium carbonate. So what will be the mass of magnesium carbonate there in terms of X? Right? As the molar weight of magnesium carbonate is equal to 24, 12 and 48, altogether is 84, and the molar weight of calcium carbonate is equal to 40, 12 and 48 is 100. Right? The mass of sample is going to be the G mole minus 1 value into mole value. The G mole minus 1 value into mole value will cancel off the mole term and you will come up with some G. So 84 G mole minus 1 into X moles will give you the mass of calcium carbonate there. So it is going to be 84X. 84X. This is the mass of magnesium carbonate in your sample. Like that, the mass of calcium carbonate in your sample is going to be 100 into Y. 100 into Y. 100 into Y. 100 G mole minus 1 into Y moles. That is the mass of calcium carbonate in your sample. So it is going to be 100 into Y. In grams, that will be equal to the grams value provided here, 46.8. 46.8. Right? All the things are in grams. So I'm not going to write the G unit there because units will cancel off, right? All the things are in grams. So that is why I put here the G grams. So this is your first simultaneous equation. So we need two simultaneous equations to completely solve for two unknowns, right? First thing is done now. The first simultaneous equation is done now. Right? These are steps to follow, right? This is the first simultaneous equation. Right. Let's copy the second simultaneous equation here. So how to copy the second simultaneous equation? Second one. So second simultaneous equation should be built up with the use of the second data point. That data point is about the CO2. So I earlier said the simultaneous equations can be built up only for masses or for moles. So this is for the mass of the sample. Now we could think of mass or moles of CO2, right? So this is regarding CO2, the second data point. So it should be mass or moles of CO2. So here they have given us some other data. So they are telling us that volume of 1 mole is equal to 22.4. Volume of 1 mole is equal to 22.4. So that we can convert this decimeter cube value for the moles. So they have given us some relationship between the moles and the volume. Right? So this volume can be now converted into moles, right? So we can do so. So let's copy the second simultaneous equation as then amount of moles of CO2. Right? The second simultaneous equation is for moles of CO2 gas. Right? Let's copy those values. Right? So 1 mole of gas is equal to 22.4 decimeter cubes. So it's like this now. So if you think of decimeter cubes and the moles, 22.4 decimeter cubes represent 1 mole. Now we have 11.2 decimeter cubes. So 11.2 decimeter cubes should represent, right, this. So 22.4 into 11.2. That's right now. So 22.4 portions represent 1. We need such 11.2 portions. So per one portion, it is 1 over 22.4. 11.2 portions means that into 11.2, right? That value will be given as what? 0.5, no? 0.5. So we can come up with the second simultaneous equation now. So the number of moles of CO2 in terms of x and y is the x plus y. Number of moles of CO2 in terms of x and y is the x plus y. So that value is now equal to 0.5. 0.5. That is our second simultaneous equation. Right? Two simultaneous equations are written now. Right? One for the mass of the sample for the first data point, and second one is for the amount of gas in moles, right? So two simultaneous equations are built up with the use of two data points, right? Now we have two simultaneous equations in terms of x and y. Now what we need to do is just solve those things to come up with x and y. If you are to solve the x and y, then we can come up with the masses as g mole minus 1 data are known. That will lead you to the weight percentage, right? Okay, let's try to solve the two simultaneous equations, right? So number 4, the fourth thing, no? The fourth thing is solving simultaneous equations. I'll solve that here. I'll solve that here, right? Number 4 thing, no? What we are doing. Solve for x and y. Solving for x and y. Right? So what we can do? So basically, there are two methods, right? Equalizing the coefficients, that method, or substitution method. Substitution method. So the equalizing coefficient methods. I'm coming up with equalizing the coefficient methods, right? Okay. So you have 84x 100y. So I'll multiply the second thing with 100. So the y's coefficient will be equal. Right? I'll multiply the second thing with 100, right? I'll multiply the second thing with 100, and I'll deduct the 1 from that thing. So what I'm doing is I'm multiplying the second equation with 100 minus the first equation. That is the mathematical operation I'm doing here, right? Multiplying the second equation with 100 means you will have the 100y and the 100x, and I am deducting the 1. So the 100y to 100y will cancel off, right? And x will remain. So we'll have the 100x minus the 84x. Just writing the x is enough, because we have done this operation to cancel off the y. So no need of writing the y again, right? Just writing the other species enough, right? Okay, with multiplying with 100 will give you here the 50, that minus 1, equation 1. Equation 1 means this value 46.8. So that will give you 16x is equal to 3.2. So your x value is equal to 0.2 moles. This is your x. And so we can substitute this value here to come up with y. So that y is going to be equal to, substitute value here. So y is actually 0.5 minus 6. So 0.5 minus 0.2 is 0.3. So x and y values are known now. This is the fourth step, step 4 of the calculation. Right? Let's do the step 5. The finalizing stuff. Right? Achieving the goal. Achieving the goal, right? So now we know the number of moles, right? So we can come up with the mass of magnesium carbonate. That is equal to 0.2 moles are there, and the G mole minus 1 value of magnesium carbonate is 84. So the value is going to be, right, 164. That means 16.8. 168, no? Yeah, 6.8 grams. The percentage of magnesium carbonate is then 16.8 grams over the total mass is 46.8 into 100, no? So that will be given as, let's do the calculation here, 16.8 divided by 46.8. That will be 35.89 into 100, right? This 35 point, I'll come with 9 as the mass percentage, right? So what about the calcium carbonate stuff then? So you can take the 100 minus magnesium carbonate, because only those two are available, or you can come up with the normal way of calculation. That means calcium carbonate mass is actually 0.3 moles are there. That's G mole minus 1 value is 100 G mole minus 1. That will give you 30 grams, right? The rest of the grams, no? From the 46.8, right? So that you can copy the WOW value for calcium carbonate. That is 30 grams over 46.8 grams into 100. So the value is, well, it should be 64.1 then. Right now? So that is how we are supposed to solve this kind of a question, right? Okay, so let's go to the solving here. You can copy it down. Let's discuss the question number 2, right? So you see the question appearing here. Let's try to solve this one. Right, here what they are saying, 25.6 grams of solid containing only calcium carbonate and aluminum hydroxide was completely thermally decomposed, and you got this data, right? Okay, so first thing here is actually identifying the goal for any this kind of complex calculation, complex procedure. What we are doing first is actually identifying the goal. Mainly, the goal will be there at the beginning of the question, at the first two lines or at the last two lines. Let's see what we need to do, what we are supposed to come up with, right? See, at the first two lines, it is not there, right? 25 grams of some data given, but if you are to go through this, calculate the mass percentage of aluminum hydroxide and the calcium carbonate in this example. That is actually your goal, right? This is actually your goal, right? Calculating the mass percentage of aluminum hydroxide and calcium carbonate in your sample. This is your goal, right? The two related chemicals in your goal is these two guys. It could be 2 or 3 normally in your calculations, right? Here you have two related chemicals with your goal, right? So first thing to do is actually take them as x moles and y moles. That is referred to as identifying the goal, right? So let right, aluminium hydroxide number of moles equals x moles and calcium carbonate number of moles equals y moles, right, in 25.6 grams of sample. Right, that is your goal. Identify the goal. So, and put x moles, y moles for the two chemicals appearing in the goal. Right, that is done. The first step is done. Second step, then you have to come up with the chemical equations, the balanced chemical equations related to the procedure. Right, let's try to come up with those related balanced chemical equations. Right, here what they have done is actually they had decomposed the calcium carbonate and aluminum hydroxide. That is what they have done, right? So let's try to write the two decomposition reactions for the calcium carbonate and the aluminum hydroxide, right? So the two decomposition reactions, right? So aluminium, sorry, as I'm taking the aluminum hydroxide as X, I'll take the aluminum hydroxide first, right? So aluminum hydroxide decomposition. So aluminum hydroxide comes under, the aluminum comes under moderately active metals. So their decompositions will give you the respective oxides, the aluminum oxide and the hydrogen oxide. So aluminum oxide, the Al3 plus O2 minus. Al3 plus oxide is the O2 minus. So aluminum oxide, and the hydrogen oxide is H2O. Will be as a gas, right? Metal oxides are always solids. H2O most of times released as a gas, right? You are starting with a solid, right? Okay. So what about the calcium carbonate? The second one is the calcium carbonate. That decomposition will give you the calcium oxide and the carbon oxide, right? Calcium oxide and the carbon oxide is carbon dioxide, right? Okay, those are the two stuff, right? And they are saying the volume of 1 mole of gas under STP. So STP means the STP means standard temperature and pressure, right? So pressure means 180 m actually. At standard temperature normally comes with 0 Celsius in gaseous situation, right? So that at that situation, H2O is not going to be a gas. H2O is not going to be a gas. H2O is actually solid, right? So at 0 Celsius, right? It is not going to be a gas. So the only gas you will come up at the STP is the CO2, right? The only gas you will come up with at STP is the CO2. we have to consider that because they have collected the gas at STP situation, right? Okay, that is the situation, right? So only gas is CO2. So we had written the chemical equations, the balanced chemical equations. So we had to balance the stuff, right? Sorry. So you have 2 aluminiums, so have to complete 2 here, some 6 hydrogens and the 6 oxygens. So for that 3 is needed here, right now. And for this one, actually it is balanced, right? So the second step of the calculation is done, coming up with the balanced chemical reactions, right? The third step of solving the problem. So as the third step, we need to come up with the simultaneous equation, right? Simultaneous equation, right? To completely solve for 2 unknowns, right? 2 unknowns, we need to come up with 2 simultaneous equations. So to write simultaneous equations, we need to first identify the data points. What are data points? Data points are the numerical values, right, of species we completely know. Numerical values of chemical species we completely know. We should definitely know what chemical species are appearing with that number or with that numbers, right? So then it can be considered as a data point, right? So here we should have 2 data points to come up with 2 equations, simultaneous equations. Definitely there should be 2 data points. Let's try to come up with those, right? So what are the 2 data points appearing here, right? One data point appearing here is this thing, no? 25.6 grams. So we know about this one. That is actually the total mass of the solid sample. That is the total mass of the solid sample, right? So this is the total mass of sample. It is one data point. We can come up with a simultaneous equation for that data point. The second data point, what is the second data point? So they have given us some volume here, volume of the gas collected, right, at STP. So this is some second data point, the second numerical value, which we know completely about the chemical appearing with the 2.24 decimeter cubes. So actually that is the amount of the gas released here. So the gas is CO2. The only gas at this TP is the CO2. So this is referring to the amount of CO2. Right? Okay, those are 2 data points. Let's try to come up with simultaneous equation for those. Right? First simultaneous equation. It is for the total mass of sample. So it is for total mass of sample, or the mass of sample. Or let's say for the mass of sample. Let's better write like that. For the mass of sample. So we are writing these numbers in grams. So if you are indicating like this, the unit, no need of writing the units in the simultaneous equation, because at the both sides the same units are used, so that units will be cancelled off, right? So total mass of sample. So total mass of sample is due to the 2 species there, right? The mass of calcium carbonate and the mass of aluminum hydroxide will give you the total mass of sample. So as we know the values in terms of x and y, the moles, we need to first come up with g mole minus 1 data, right, to relate them to the moles and come up with grams, right? So first let's calculate the g mole minus 1 data. So mole weight of aluminum hydroxide, that is going to be this 27. You have 16 plus 17 into 3 is 51, and 27 it is 78. What about the calcium carbonate? Very common value, right? 40, 12 and 48 here, so it is 100. The total mass of sample is then going to be the summation of the masses of these two guys, right? These two guys, right? So first of all, the mass of aluminum hydroxide can be written as is G mole minus 1 data into its number of moles. So it is going to be, right, 78 into x, 78 into x, 78 G mole minus 1, number of moles is x moles. So mole minus 1 and mole will cancel off to come up with the value in terms of G, right? Like that, for the calcium carbonate mass, it is going to be 100 Y, 100 G mole minus 1 into Y moles. The moles terms will cancel off as mole and mole minus 1 are there. So it comes as then 100 Y grams. So we are not writing the grams terms because those will cancel off with the both sides of the equal sign, right? So that value is equal to the data point that is 25.6. That is your first simultaneous equation. So first simultaneous equation, right now? Right. Let's copy the second simultaneous equation. Right? So this is x moles, this y moles. Huh? So second simultaneous equation can be written for the amount of CO2. Basically, I have told you earlier at the earlier question as well, simultaneous equations can be developed only for the masses or only for the moles. Only for masses or moles. You can develop the simultaneous equations. So this was about the mass of sample, right? So we need to come up with some mass of CO2 or moles of CO2 for this data point, right? So basically, these decimeter cubes, right, will be related to moles, with this relationship. 1 mole of gas under this Tp is 22.4, right? So we can relate that thing. So we can come up with some simultaneous equation for moles of CO2 gas. Right? So first of all, at the left hand side of the equal sign, you need to compare in terms of x and y, the numbers in terms of x and y. At the right hand side of the equal sign, we need to come with a numerical value, right? Okay, that is the idea now. So as the left hand side, you need to come up with x and y, and the right hand side numerical value. First of all, let's come up with this thing. Let's convert this value for the towards moles, right? So decimeter cubes and moles. So 22.4 decimeter cubes representing 1 mole. So 22.4 portions are for 1 mole. So now we have 2.24 portions. So that is for, actually, 1 divided by 22.4 will give you for 1 portion. We need such 2.24 portions. So that value is going to be 0.1. Right now? So that we can come up with the second simultaneous equation here. In terms of x and y, the CO2's value is what? You have y here. So 1:1 ratio. So this is also y. So y. 1:1 ratio. That is the only gas available there. So it is the y here. In terms of x and y, the CO2's number of moles is actually y. It is equal to 0.1. From the other side, it is equal to 0.1 as a number. So the y's number is solved there. 0.1 moles. Y is 0.1 moles. Right? Okay. Coming up with simultaneous equation. So that is actually second simultaneous equation, no? Okay. Y's value is actually given by that equation, right? Okay. That is the completion of the third step of the calculation. First, we have identified the goal, came up with the balanced chemical equations, then build up the two simultaneous equations. Fourth thing we should do is solving for x and y. Solving for x and y. Right? The fourth thing we are supposed to do here is, right, solving for x and y. Sorry. So y is solved from the equation 2. So just substitute that value for the 1. One will give you 78x plus 0.1 into 100 will give you 10 is equal to 25.6. Right now, 25.6 there. So this comes to here. So 78x is going to be 15.6. So x is then going to be 0.41. It is 2, no? That is the value of x, 0.2. So that is solving for x and y. Next stuff, achieving the goal, right? So that we can come up with the masses of aluminum hydroxide as well as calcium carbonate now, as we know the mole values, right? So aluminum hydroxide mass is equal to, its number of moles is 0.2. Its molar weight is actually 78 grams. It's 78 g mole minus 1, that's molar weight. So it is going to be, right, 15.6, no? Grams there. 15.6 grams there. So percentage of aluminum hydroxide is equal to 15.6 grams divided by the total mass is 25.6 into 100. So that value can be simplified. So it is 15.6 divided by 25.6, no? That is 60.9 as a percentage, right? That is aluminum hydroxide. Let's do the same for the calcium carbonate as well. So one can write as only the calcium carbonates and aluminum hydroxide are there. So one can write the percentage of calcium carbonate as 100 minus 60.9, as only those two guys are there, right? It is going to be 39.1, no? Almost 39.1. Right, no? Okay, that is those are the solutions for the Roman number 1 of your question. Roman number 1 of your question. And ultimately what they ask is, calculate the mass of aluminum oxide produced after the complete decomposition. Calculate the mass of aluminum hydroxide. So what we can say, number 2, before the aluminum oxide mass, first we'll come up with the aluminum oxide moles. That is equal to, so aluminum hydroxide to aluminum oxide is actually 2:1 ratio. If this is x moles, it is going to be XO2 moles. XO2 moles, right? So that value is XO2 moles. XO2, that means the X value is 0.2. 0.2 is the X value over 2. This is 0.1 moles. So now we can come up with the mass. Mass is equal to 0.1 moles into its G mole minus 1 value. What is the G mole minus 1 value? 2 27s are there, 54, and here 48 is there. 48 is there, no? 48 and 54, that is 102. So that value is going to be 10.2 grams. 10.2 grams, no? That is the value for aluminum oxide mass. Just complete the question now. Okay, Lamai. From this section, right, that is actually the end of the session for the thermal decomposition trends, right? You have some questions appearing at the page number, which one? So just go to the tute, right? And they are at the page number 31. So at the page number 31, right, you have the question number 6 and 7. Question 6 and 7 can be done, right? Those are related to the thermal decomposition trends, and do those two questions at home, right? Page number 31, the question number 6 and 7, right? So with that, we can wind up for the today's session regarding the thermal decomposition trends, right? So until we meet, goodbye then.